Day 7 of not only Nodevember, but No Nut November is proving to be extremely difficult, extremely hard. Might be a better way to put it, pun intended. But the prompt for today is printing, and I thought, you know what, why not just not do what everybody else is doing with the printer and the vector displacement and all that, but try something a bit more unique. So you can see I did a teleportation, which is pretty fucking sick. Let's not let that slide. This is a pretty cool looking effect. You can actually do it between any two objects. It doesn't have to be spheres. And again, the interesting thing about this is it's all starting off with a cube that is vector displaced to look like it's two objects kind of printing each other out, transmuting. And yeah, we got to do something more interesting. I mean, I thought food was bad, but textures is proving to be pretty boring as well. I'm looking forward to time, especially cyberpunk and all that. So how do we do this? I'm going to try to make this tutorial slightly faster than some of the others, because lately they've been like an hour, if not more. And yeah, that might be a bit too long, don't you think? Okay. So speeding ahead, here's the blend file again. This is the completed project, the one that I rendered. It exists on Patreon. Let's just, get that out of the way. Get that advertisement just so fucking far away we never have to mention it again. We're going to do our best to kind of duplicate this effect. And by the way, and this is kind of an interesting point, notice that there's this tendril connecting these two spheres. This is going to be the trick that lets us render these like they're two different looking objects, even though they're actually connected. We'll talk about that. It has to do with transparency and all that, which is a new technique. But what is it that we actually want to control? Well, first of all, we need a printer slider. This is saying, which sphere is going to be active, and they move at the same rate is kind of the point. We have the transform from the cube over to our vector displaced version. And by the way, the cube looks pretty sick. We have spacing for how far apart these are going to transform, and then we can also control the aspects of our kind of effect over here, okay? And then, of course, I animated it and all this. Okay, new project. Enough of that. Enough rambling. Let's get started. I'm using Blender version 2.92. You can use version 3 if that has come out by the time that... But point is, use 2.92 as well to make sure everything's working. First of all, we're going to get rid of our light, and we want to set up an HDRI. This is for the kind of veteran viewers who are here with me on day 7 of Nodevember. Kudos to you, by the way. It is getting difficult to do it every day. For those of you who have come this far, we're doing the same setup as always. So HDRI, add some Control 3, Subdivision, Surface of Level 3, set to Simple, just so we have more geometry to work with. Material, make sure that the settings have, as always, I guess we need to be in cycles to have this, our displacement settings. So just enable all these beep boops, buttons, boom. Make sure that your material has some kind of displacement enable. So settings, displacement only is better than displacement and bump, so that we don't get shading artifacts, etc. Okay. Now that we have our scene set up, let's actually save this and give it a unique name, like I have a Patreon, of course. Now that we've done our setup, we need to just talk about the name of the game. How do we get two separate objects from one and make them transform and all that, okay? Surprisingly simple, actually, but it does take a bit of theory, right? So we're going to take the cube, we're going to transform it to a sphere the same way we've been doing every single time. Once we have it into a sphere, we're going to do kind of like mitosis, like two cells splitting, like, your parents have just, they've done the thing, you might be getting a new sibling, right? And then the cells are starting to do the mitosis and all that. So now we have two spheres. We're going to separate them apart using a transparency trick, and then finally do the laser stuff to get one to appear where the other disappears, okay? So that is the game plan. However, even though that sounds a bit complicated, we do start the same way we've always been starting, using generated coordinates again, because those actually stick with any vector displacement we're doing, whereas the rest of these don't. But we do want to transform our generated coordinates so they look like object coordinates, or similarly, the position coordinates of the geometry node, which is the same as object coordinates when the object is centered, okay? Okay, cool. Enough theory. Let's actually do that. Vector math. First of all, we need to transform it so the origin is at the center of the object. Boom. That does that. And then let's also scale by 2. This is not even a burp like I hate. This is a burp like I want Chipotle. It's like a anticipatory making gas leave the stomach so I have more room to stuff myself sick. Again, what's happening here is we have generated coordinates that uses the bounding box. So the origin should be over here in the corner somewhere. We want to transform it to the center, which means we need to move it by the vector 0.5, 0.5, 0.5. So just subtract that away. Boom. And then we scale it so that x, y, z have the interval 0 to 1 in each direction, right? So now object coordinates are indistinguishable from what we have made, although this version is made off of generated coordinates. Boom, node group. Never have to look at that or make it again. So this is going to be our first step, the coordinates. And let's actually make 2 instances of these, and you'll find out why in a second. Okay, so first order of operations, first step is turning this into a sphere before we do the mitosis. Again, seems like it'd be a complicated mathematical formula, the kind of thing that you're going to have to devote your life to, and you might not even prove the theorem, right? No, it's super simple. Sphere is just a set of points that are equidistant. The vectors that make it up are the same length from a certain point, okay? So the way we do that, the way we represent that, is we want to take all these coordinates of our cube. Again, they look like this. We want to output the length, which right now are not equidistant. The corner has a bigger length than some other point, right? We want to say we want to do a normalization, so we're going to multiply by the reciprocal. Actually, we're just going to divide. So we're getting 1 over the length, so that's the reciprocal. And then if we scale by this value, everything's being normalized over to 1. And I guess, to be honest, so first of all, let me do it like this and then kind of theory craft about a simpler way to do it that I've just like thought about now. Maybe I've been wasting my time. Let's see. So this gives us the transformation, but we don't want to plug this into displacement because, again, we want displacement information, not like where the final coordinates are going to be, because right now we have the cube, we're doing a transformation, and then it's adding the initial coordinates, right? So this should only be talking about change, not the final output. So again, we just need to subtract away the initial places. So we only have the displacement, the change, not the final output, which works. But what I was thinking just now is, could we have just done this with a single node? Is this going to be a historic moment? I'm thinking what we can do is, instead of this, maybe we can scale it not by 1, but normalize it. And that makes a sphere as well. Who would have thought? This is kind of like a compact way to do the same trick. So from now on, I guess we're going to be doing normalization. I cannot believe I thought about that on the fly. But you know what? Sometimes it just be like that. So again, what's happening here is we have our geometry that is being transformed into the sphere. And we can actually see that process if we scale, if we can find scale, because it's hidden. It's like pirate treasure we're trying to find. There we go. You see the geometry is being transformed in a normalization way, meaning all those vectors are being created with magnitude 1, okay? Last thing I like to do with these kinds of setups is, since we're going to be connecting stuff into the socket over and over again, because we always do need to subtract coordinates at the end, let's give this a bit of color so that we can reference it later. Copy that, and I'll do the same thing here. Okay, step 1 complete. Congratulations, we did it. Now what we need to do is kind of the new idea, and this is a trick that I think originally is Simon Thomas's. It's his, right? He taught Gabe taught me, and bada bing, bada boom, and now you're gonna learn how to do it. To turn this sphere into 2 spheres, which is that trick, you might think we need to do a lot of math, but it's actually one of the simplest transformations, almost as easy as this normalization. What we're going to do is we're first of all going to separate by x, y, z and look at the x-axis, so we see this gradient. We're then going to take this, we're going to take a absolute value so it has symmetry. Again, this was a 0 to 1 over here, and then like 0 to -1. That's the gradient. When you take the absolute value, these are mapped to positive values, which kind of makes it look symmetric along the x-axis. In fact, it is symmetric. And turns out human faces aren't symmetric. You you kind of cut out 1/2 of a person's face and flip it so it's perfectly even. They start looking like aliens. It's the asymmetry that you can't see that makes stuff look realistic, but forget about that. We're just going to be dealing with symmetry here. What we do is we take this. So again, we have this gradient that goes from 1 to 0 to 1. And then the trick is, and I'll explain it in a second, is we take, again, the last thing we do before we reach the subtraction. We're going to scale it by, I believe it's just absolute value. It might be the reciprocal. No, it's actually just absolute value, and that gives us 2 spheres. And you might be thinking, okay, that's some true witchcraft, and it is. Thank you, Simon Thomas. It's hard to say that name. Thank you, Gabe, for this trick. The reason it works, again, is we have this sphere. We've created this map, again, using the absolute value, and if this is what we are scaling by, notice that at the middle it's black. In other words, it's pinching it to 0. In other words, this is going to be the connection point because it's pinching those vectors to 0. And as we progress, stuff is going to get smaller and smaller and smaller until we get to the halfway point, and these are going to be kind of the top of the spheres. And then we kind of scale back up to 1, so these aren't affected. In other words, we get the perfect amount of linear gradient so that it pinches here, has this be the halfway point and this be remain constant so that it works, right? If we were to do anything else, it would not work, right? So if we did like a map range and just modified this interval a little, we could do something like this, and you see that it would start reforming the shape. Or if we did a different type of interpolation, you see it's going to give a different kind of silhouette. So there really is something special about the linear thing here. You could think about it until your brain goes numb and falls out your mouth socket and you have somebody clean it up, right? You could think about it, or you could just take my word for it. It does work, okay? So now we have the second transformation. This is going to be our... So let's just connect everything here and group this up. And I'm going to include the normalization here. So this is not only our to sphere command, but it's also our like doubling of spheres. So I'm just going to call it... Whoops, not sphere, but spheres as in multiple, okay? And we don't actually, we don't actually need this absolute value. So I'm going to take this and remove it from the outputs, okay? So now what we have is the cube that is transformed into a sphere and doubled up to look like, kind of like a ball sack. I guess there really is no other way to put that. I was trying not to say it, but it was on the tip of our tongues, the tip of our penises almost, okay. Cool. So now we have two spheres, and now the question is, how do we separate them from each other? Because if we were to do some vector math to move them over, it actually moves them together, right? So it looks like two meshes, but it's technically one mesh connected at a infinitely thin connection point, because again, it's scaled to 0 here, okay? So the question is, how do we handle it? And the answer is, instead of one vector displacement, we have two. One for this sphere, one for this one. And we're going to not min-max, so we're going to mask it out. So separate x, y, z. Look at the x-axis. So again, we're separating left from right. An easy way to do this very quickly is a greater than 0. So we're saying which points to the right are greater than 0 and which of them aren't. And now we've created a mask separating one or the other. And I guess while we're here, we could do a opposite mask as well. However, I'm not really seeing the value in that. For now, let's just use this. And now we're going to, once we use it, we're going to talk about another mask that we're going to need in a second once we actually separate these away. But for now, what we could do, some vector math, some addition. So we're going to be moving these but not together by some kind of mixing factor that we're going to set up, okay? So let's connect this here. And we just need to do some magic to this x-axis so it's not the same everywhere, okay? So what I'm going to do is we could do a mixing factor. So let's do mix RGB. This is going to be our factor right here. So we could have like two different colors. You can see how this kind of separates the information. And I'm thinking for one of these, we're going to have a value describing the distance we want this to be away. And for the other, I guess we just kind of take the negative version. So it's actually going in the other direction. So multiply by -1. Boom. And now we have this thing that we could connect to is it x-axis? Yes, x-axis, and they might be flipped. There we go. So now with a single slider, I guess I should have connected it here. With a single slider, we've actually created separation. Again, why does this work? It works because we're saying add 0.5, as in basically take the sphere and move it 0.5 to the right. And for this one, do it by -1. So -5, or 5 to the left, which are mixed together. So these instructions aren't the same for both of these by this mixing factor, okay? So that is the big deal. Now we have vector displacement that can be separated, and different instructions can be given to different things. But of course, we do have the issue of this connection point, which, again, should be kind of like infinitesimally small because we scaled by 0 back when we made our absolute value map, right? So it should work. However, let me actually get rid of that. I keep doing that accidentally. However, in practice, it doesn't actually work that way because we need a bunch of geometry around these poles so that it doesn't need to kind of borrow geometry. So in other words, the more geometry we add, the thinner this is going to get. So let's change to experimental, do adaptive subdivision, which is going to give us much more division on the fly. And what we could do is just take this down to a smaller dicing scale. So for every pixel, in some sense, for every pixel, there should be more divisions, kind of like subdivide my life. Mess it up, right? The smaller the number this is, the better we have it. And to make sure that this is invisible, that's just going to be BSDF stuff, and we can mix this with a transparent shader, right? So transparent BSDF, mix these together. How do we want to mix them together? With a mask that's not this one, separating them, but the mask saying where is the point in between, right? So let's use compare to do that. We're going to compare by 0 and say which points. In other words, when we compare to 0 and use an epsilon, what we're doing here is we're saying look at these x and say which points are within distance 0.02 of 0, right? If we were to change this, it'd like move over from left to right. but we're comparing it exactly to the center point of our absolute value, and we're saying which is within this, which points are within this threshold. And the smaller we make it, the less of our circle is going to be taken up. And again, the point here is you can use this as a transparent thing, and now these kind of look like they are separate objects. And we want to seal those holes, again, by making this mask more and more intense. However, you're going to see that when we make it too small, so let's kind of keep going until it starts breaking. When we make it too small, you're going to see some of that geometry returns. So you can either add more divisions, and generally that is what you have to do, or sometimes it might just be that Cycles isn't calculating enough transparency passes. That's possible too, you know. The multiple sides to the same coin, more than two even. So transparency might want to bump that up, and that's just going to give you a bit more to work with. I guess in this case it doesn't help, but let's lower this even more. But when you do this and you still see some points poking out, it does help to give more transparency passes, so Cycles has more to work with. But for now, I think we can accept this, and on render we can make that point even smaller. So what do we have so far? What we have is a setup with vector displacement that kind of separates this area in between. That can be of arbitrary thickness, or thinness really. And with our vector displacement, those are mapped to two little dots there and there, which again, we do have this issue. So I'm just going to bump this up to 20, and that's probably going to help on render. But for now, you just have to imagine that this connecting strip is not here, okay? And on top of that, with our vector displacement, we also have a slider for this, okay? So let's make this a node group. I want to control, again, the separation, and let's also control the threshold, because that's going to be important for making this cutout very small. So take all these, group them together, Control G, boom, now we have our next situation. So we have our coordinates, we turn them into spheres, and then finally, on day 7, on this historic moment of Nodevember, we have, what is this? What did we do? We did the mitosis step, the cells in your parents, that whole story. And now that kind of leaves us with one final thing, which is this idea of, again, we're going to use transparency just like we did in the middle here, but we're going to use transparency to cut into these spheres. So as one appears, another disappears, etc. And we also need the laser. Okay, so what is this value? Why did we keep that? Oh, for our mixing factor, of course. Maybe we should give that a name so I don't ask that again in the future. So this is going to be our strand. That's the connecting point. Okay? Okay, so name of the game now is basically a bunch of BSDF stuff. Since the vector displacement's really done, we don't need anything beyond the spheres, beyond these, unless you want one of them to be a monkey or something, you could do that too. But beyond that, it's just some BSDF stuff. So, like always, we're going to separate by X, Y, Z, and we want to make kind of like the laser effect going up here. And as it goes up here, conversely or inversely, one yin and yang, one goes up, one goes down. Harold and Kumar, light and dark, apples and oranges, CG Matter. Wow, failed that one. CG Matter and Blunder Guru. I choked saying my own thing. As one laser goes up, we want the other to go down. We can use this by taking the Z component, and just like last time, if we want a small strand, we're just going to use the compare function. So we're comparing the Z axis to, I guess, 0.5, or I guess 0 if you want it to be centered, with a thickness of this. And notice that since the strand is in the middle, it's actually also being included, but it is going to be transparent, so don't worry about it. Okay, so let's make that a bit thinner. We can always control that later. And now we need some way so that this value is different from one side to another. So as this goes up, this goes down, so it can't be the same on left and right. And to do that, I believe we can just use our mixing factor from before, which, where is it? Is it in here? This, I'm looking for the one that separates left and right. I know it exists somewhere in here. Is it this node? Yes, I guess it is here. Am I losing my mind? I feel like I'm losing my mind. This happened during the sphere step. So yeah, we could do it from here. We can extract it from here. So we can do another separate X, Y, Z. I guess we kind of lost that map before, or I'm just losing my mind. We're going to do a math greater than 0. So this is going to be our separation, not hyperbolic sign who uses that one. This is going to be our separation mask. And again, what we want to do is have different values from one side to the other. Okay. To do this, we're going to do a mix RGB. Mix RGB. Boom. Make that the factor. We're going to connect this here. so that it's actually affecting this. And then for the slider, we need one value here. And this is going to take a bit of finagling to figure out what's going on. So as this goes up, we have control of the right side, but the bottom side's determined. And I think we want the subtraction version of it. So again, we don't want the same thing on left and right, because this is saying what's going to be on the left, what's going to be on the right. They shouldn't be the same thing. I think on the other side, we need 1 minus this. I guess we'll figure it out on the fly. Or maybe it's the multiplication by -1, because we're kind of parenting over the z-axis. Let's see, or reflecting over. Let's see how that works. Yeah, there we go. So now we kind of have the opposite thing going on. Again, why does this work? Because when this is equal to 0, you multiply by -1, so it's the same everywhere. When we increase it to anything else, as we go to 0.17 here, you're going to the opposite negative on the other side, and now you have these nice bands. I guess we get rid of this, and now it should work. So now 0, and then we increase. Okay, beautiful. It took a bit of finagling, but what else is new here? Okay, so now we have a slider that lets us control the laser beam. So let's actually just call it that. Boom. Okay, so again, moral of the story here is we have 0 to 1, and we map it to 0.5 to -0.5, because that's exactly where the cutoff happens here, okay? To make it a bit more interesting, what we could do is add in a bit of noise, so they're not just these perfect lines, right? So what we want to do is before this reaches the compare, we want to just add in a bit of noise to noisen this up a bit. We mix these together with a linear light. Again, this is the idea of noise adding on average 0.5 everywhere, because it's going to be adding some number between 0 and 1 on each point on the sphere. So on average, it's adding 0.5. Linear light corrects for this. And we can control the kind of magnitude or the strength of this noise. So you can see when it's 0, it's kind of a straight line. And otherwise, we just get a tiny bit of useful distortion, okay? And similarly, we can still control this with the value slider. Only thing to consider now is maybe -0.5 to 0.5 isn't enough, because the distortion makes it so that there's just a tiny bit poking out when it's there. So let's just go to 5.5 and -5.5. That should be closer at least. So now when we're at 0, yes, it's off the sphere. Okay, cool. Some other stuff with the noise is maybe add in some detail, so that when we add in roughness, it's just going to look a bit more interesting. So it's now a nice jagged line. And then otherwise, now what we need to do is, it's all going crazy. What we could do is right now just set this to have a emission over it. So this is before we do our transparency command. It doesn't really matter the order of operations, since this is just isolating the strand, but for the emission, we want to say, do the emission with the mixing factor of this thing we just made. Whoops, connect that there. And now we have exactly the same setup that we would want minus the transparency, right? So let's make the emission red and way stronger. Oh, these are flipped. Red and way stronger, just so it's glowing a bit and it's not as intense. So something like this. And yeah, there you go. So now the next step is making it so that one appears and one disappears in the exact same order that it should be. So in other words, as one reveals, the other one disappears, still keeping that inverse relationship. And to do that, we just need to make another kind of factor. And for this one, it's pretty simple. We just do a greater than kind of situation where we're saying this kind of value, this thing that we calculated before, we need to use it again and just compare it to the height of the z. In other words, and if you're not really following what this is doing, it's going to create a mask where this is kind of centered on the laser beam, so that's why it works. A mask where this should be kind of the inverse relationship. It's looking like it's working for sure. So just to test that theory, what we're going to do is add another transparent BSDF right here, mix these together before it reaches the emission. So again, the laser is going to be above this effect. Put this in here, and it's either going to give us the correct thing or the exact opposite. Let's see. So now we do have hemisphere, so it is actually making it transparent, and it does seem to be working. And you could also do a flipped version of this if you wanted, going the other way, so that's a less than. Or you could actually have one kind of doing the literal opposite of another, so you could have one greater than and one less than. I don't know which one I actually did in mine. Can't remember, but it's basically the same setup. You connect Z over here. You mix these together, mix it with what? With our factor, separating left from right, and then this should give us the exact reciprocal relationship. You know, thinking about maybe this is the one I did. That is definitely possible. Okay, so now we have the basic setup, and now the question is, how do we take this and finally make it look, cool? How do we make our laser look crazy? You might think that it's difficult, but not really. All I did is I added in a Voronoi section. I think I just mixed these two noises together. Also, something to consider, I didn't talk about this before, always use the last vector displacement step as the coordinate system. Just so it's mapped correctly. And then I think what I did here is I just literally mixed these together, same idea from before, use a linear light. And then we could actually increase, there we go. We can increase the effect of this, make the scale of the Voronoi bigger. This is what gives you the chunks. And then finally, I think I set this to Chebyshev so that we have those nice little fragments, etc. And I think, in essence, this is what I did. Maybe I made a separate mask for one versus the other. So the laser isn't affected by one, but I don't know. Point is, now we have a procedural way to make it look like it's materializing in a way that it's connecting polygons and stuff like that. And really the name of the game for the rest of this is just making it look good, like adding a bit of a fall off here using a subtraction mask. So again, it kind of browns before it gets there. So it'd just be something like this is the way you make that mask. So you just want to pick a value so you can see that it's changing as we move this value. And this is just the thing I used for the burning, but yeah, in some sense, that is just the essence of the effect. I knew this would be a quick one. I didn't realize it would be this quick. There you go. Let's see the final result. You can see how we get from one to the other. I think I might have actually chained together two different noises, one with Chebyshev, one with Minkowski. But again, vector displacement, it's one object. And when we render this again with all the transparency passes and geometry, it gets rid of that fragment in the middle. Actually, let me just show that. So you know it's a reality. I guess you can already see it, but just to verify, if we hit render, you're going to see as long as we have that transparency mixed together. Oh no, we have too much geometry. It's going to crash Blender. Oh no. Make sure that this is set to something like a 1 or higher if your GPU's garbage. You can see these are actually separated. You can make that mask thinner. But end of the day, that's how you do it. If you want the original blend, it exists. You can go pick that up on Patreon. Also exclusive tutorials, Discord, stuff like this. And yeah, day 7 is kind of an underwhelming one. Didn't want to do too much for the weekend. So yeah, see you.